Welcome to the continuation of the topic of plate with holes. So we are trying to solve this particular problem where you have a plate subjected to uniform tension along two opposite faces with a small hole. So in the last video lecture, what we said was this particular problem can be simplified to this particular problem. Okay, this circular disc with a hole with the loading so and so, which we had written it as the solution of two problems. So here the only thing is we are dividing the external stresses or loads in the both the cases. So here the stress becomes independent of theta, and as we had discussed in the last lecture, we had written this particular solution for this problem based on what we had seen till now for problems which are independent of theta. So now we have to solve this particular problem as well, and then we can take the sum of these two, which will be the solution for this, which will be the solution for our actual problem, which is this. Okay, so now this particular problem, it is subjected to a constant external normal stress sigma r and tau r theta, and both sigma r and tau r theta are functions of theta. Now in mechanics, advanced solid mechanics, sorry, till now, based on what we have learned, we have to try to find a solution for this. So till now our methodology has been to arrive at a stress function, first of all, which satisfies the compatibility condition, and based on boundary conditions we will solve for the problem we have. So for solving this particular problem, of course it is in polar coordinates, it is seen that the problem can be solved if you take the stress function of the following form. So the stress function phi, in this case, it is a function of r, into cos 2 theta. Okay, so how did we arrive at it? Well, it's all based on some back calculation that was done by Timoshenko and people like that. So we won't go deep into that. But here, if you take the solution in this form, then this will be satisfied. Now you might ask what is this? F of r is again a function of r, right? So here what I understand is, by taking the solution in this form, it is acknowledging that the solution is arrived at by decoupling r and theta. So here the theta term is separate and r term is separate, so there is no coupling between both. Because this is in other forms you can think of it is like both r and theta combined in different terms, so that is not possible here. Here the stress function is one particular function which is completely a function of r and a separate function of theta, which is cos 2 theta. As I told you, this is done by some back calculation, we won't be discussing that. So it is found that the solution for this particular problem is obtained if you take the stress function in the following form. Now what is f of r that we will evaluate? So for evaluating it, before that, first let us substitute it into the compatibility condition. So what is our compatibility condition? This is our compatibility condition in polar coordinates. So if you want, I'll go back to that page 71. See, this is the compatibility condition in polar coordinates. So this particular function, we substitute it into that. So f of r is a general function of r, and you have cos 2 theta. So here you take out the derivatives. So f of r, we just maintain it, means second derivative and first and second derivative of f of r with respect to r, we can just write it as it is, that's all. So we find out the individual terms and you substitute it into the compatibility equation using this stress function, you will get the final equation of the following form. So it does not simplify to anything special. It is still, one big equation that we have to deal with. Now it is found that uh, this, okay, by the way, in between, one thing that had happened is, see, this partial derivative got converted to ordinary differentials, because here the stress function is, a product of two terms, a function of r and function of theta. So it is as a result of the decoupling that we are able to write it in the following form. Okay, so now we have to work on this equation. Now it is found that this equation is satisfied if we take f of r, which is in the original stress function. If we take f of r of the following form, it is found that this particular equation is satisfied. Now again, how did this equation come about? That's not in the scope of our discussion. But anyway, so you have four constants a, b, c and d, and then it is a polynomial function in terms of r or radius. So you have r square, r raised to 4 and r square coming in the denominator. Now first thing is, we have to really check whether this indeed is a general solution which satisfies this equation. So for that, again we pull out these terms and we substitute it back into this equation. So that is what I have done here. So in the textbook, Timoshenko textbook, they are not covered those parts fully. I'll go to the page 93. So this is the equation and this is the solution that will satisfy that. So they are not done the check of back substituting it and things like that, but it is done here. So it is indeed satisfying the equation. So which means f of r taken in the following form indeed satisfies the compatibility condition, which in turn means that this is a valid stress function where f of r is having the following equation. Okay, so ultimately this is our stress function. Now once we get the stress function, we can find out sigma r, sigma theta and tau r theta using the equations that we have seen for polar coordinates. I'll go to that once again. See, these are the equations for stresses in polar coordinates in terms of the stress function. So using this, I can now find out the stress function sigma r, sorry, using stress function. Now that I have stress function, I can find out sigma r, sigma theta and tau r theta. Now the stress function has four constants, so sigma r, sigma theta and tau r theta will also have those constants. So this is the final expression for sigma r, sigma theta and tau r theta. Same things are given in the textbook. I'll go to there as well. So these are the expressions for sigma r, sigma theta and tau r theta. Now you have four constants to evaluate here, a, b, c, d. So to evaluate those constants, you will use boundary conditions. So what are the boundary conditions? Well, this is the problem that we are trying to solve. So at r equal to a, which is the inner radius, sigma r and tau r theta are 0. Those are the two conditions. And at r equal to b, which is the outer radius, sigma r is s by 2 cos 2 theta and tau r theta is minus half s sin 2 theta. So you have four conditions using which you can evaluate the four constants. So that is what I have done. So these are the four boundary conditions. So four equations, four unknowns. So it will be like 4 by 4 equation. So these are the equations. I have written just them in the matrix form. So solving this is a little tedious. Now in solving this one of the relationships we'll use is, see, the inner radius or the size of hole, we said that it is very small compared to the overall radius. So that particular condition we'll use. So it means that a by b, inner radius by outer radius, a by b, you can approximate it to 0. So you solve this 4 by 4 equation, and we, using the expression a by b equal to 0, we will get the following value for the constants: a equal to minus s by 4, b equal to 0, c equal to minus a square by 4 s, d equal to a square by 2 s. So here s is nothing but the external pressure. So this was our original s, right? That is s. And what is small a? Small a is the internal radius. So this is the expression for the constants. So once you have the expression for constants, you substitute it back into the expressions for sigma r, sigma theta and tau r theta, and you will get the expressions for sigma r, sigma theta and tau r theta as follows. So this is the complete solution for this particular problem. Now for this particular problem, we have already arrived at the solution here. Now remember that in this particular case, tau r theta is 0. So that is something we had already seen when we did problems which are symmetric with respect to theta. If you remember what we did in class, they will be 0. This is, just hold on for a second. Yes. Yeah. So tau r theta is 0 in this particular case. So now we have the solution for this as well as this. Now you can add them. So these are the two solutions. This is the solution we just arrived at after substituting the values of constants a, b, c, d, and this is the solution for the other part which is symmetric with respect to theta. You add both of them and you will get the expression for total stress. Now what is this? This is the solution for this particular problem, which is actually the solution for the original problem that we were trying to solve, the plate with a hole which is subjected to uniform tension. So here all the terms are clear. R is radius, a is the size of hole, s is the actual external stress, and theta is the angle at which you are trying to determine the stresses. So you can imagine you are measuring theta from here like this. So theta is dependent upon which radial position you are trying to measure the stress. Okay, so this is the complete solution for the problem for a plate with a hole. Now the same problem of plate with a hole has been dealt with in a different way in a different subject, but in advanced solid mechanics using the classical method of stress function and things like that. This is the solution and this is the procedure. If you have any doubts, please let me know. Thank you.